So I'm Professor Tony Addison. I think I see very few people in here who don't already know me. And, we've, in the past and also recently, we've done a lot of inorganic chemistry on various kinds of things. I think it's fair to say that the kind of work we do in my lab, which is very much synthesis and measurement based in the realm of inorganic chemistry, has to do with, for example, in these latter stages, setting ourselves a goal and trying to design a molecule that might accomplish the goal of some kind. Also, what we've done is we've looked at an existing question in the realm of inorganic or biological chemistry and asked, what can we do to design molecules that collectively address some aspect of that question. For instance, a biologist might want to know, why is it that some nickel enzymes you can really generate nickel-3 as redox species, but in others you can't? So interesting things like that. And then sometimes you make stuff just to see what happens. And it turns out that from a lot of those situations where things we didn't expect, things we couldn't have predicted happen, and we discover something new. So over the last few years, we've looked at systems, for instance, where we have more than one metal ion in a molecule, and we have electron spin-spin interactions, which lead to interesting magnetic properties. We've tried developing some metal organic frameworks. Most of our metal organic frameworks tend to collapse as soon as we try and do something useful with them, so I won't say too much about those. Most recently, we've been looking at ruthenium, nickel, copper, and ruthenium diamines, in particular ruthenium diimine chelated systems as electron transfer reagents. And some of these we've been able to make chiral. Some of the rutheniums undergo spontaneous resolution and start with achiral materials, and you can generate chiral crystals. But perhaps most importantly, one of the things I'm interested in now, and Mohammed Nazari, who's sitting here, is working on this, is the design of luminophores, molecules that glow in certain situations. So some work of the kind we've done a fair bit of. This is a tetranuclear copper complex. There are 4 coppers and turquoise here. And this is a molecule with a relatively unusual, rather interesting pattern of spin-spin interactions with the molecule, which lead to interesting magnetic properties for such molecules. And this has been for a long time an area of interest in organic chemistry today. There's a very hot area devoted to trying to synthesize individual molecules with magnets. And so molecular magnetism is one of the features that people are keen on. So as far as undergraduate research projects go, I've had a few students work very successfully on these kinds of ligands. These are called isoindolines. These are very easy to make. In this kind of isoindoline, which has pyridine groups on it, you take a mole of phthalonitrile and you basically cook it up in some way or another with 2 moles of aminopyridine, and you get this tridentate ligand system. So if you now add a metal salt to this and a mole of base take away this proton, you can make various kinds of metal complexes. And some of these, what we also do is you put metal groups at the 6th position, which sterically hinder the approach of that ligand X, and this leads to structures which are rather disordered. And we actually realize that some of these structures actually mimic the stereochemistry of copper centers that are found in zinc centers that are found in metalloenzymes. In fact, when we first discovered these small molecule structures, we went and looked for similar parallel irregular structures, and the only ones we found were in biology, actually. So we have some nice examples of that. Another isoindolene, copper isoindolene, that one of my recently former students worked on. It's a very interesting system because here we have, you can see if you're looking edge on at an isoindolene ligand, there's a copper here, and a copper here. So this is a molecule which has a cyclic molecule in effect with 3 coppers. And the thing in the middle is carbonate. And we never added carbonate to make this compound, to make this molecule. And what's happened is that this particular copper isoindolene, during the synthesis of what was intended to be something else, has absorbed a carbon dioxide molecule from the atmosphere. And so, a couple of my colleagues have already said something to you about carbon dioxide sequestration. This is an amazing superlattice because not only do 3 of these molecules bind to carbon dioxide, but you see they're also in the lattice, in the superstructured lattice as well, 3 other carbonate or bicarbonate type units. And so actually, I think we're learning from this kind of molecule, we have a nickel analog of this as well, we're learning something about how to use carbon dioxide in lattices. Right now, it costs, if you want to sequester carbon dioxide out of a power plant, for example, it costs you, I think, about $65 a tonne. We can do that with this molecule for less than $100,000 a tonne. So we're approaching competitiveness, we reckon. Now, one of the things we've been involved in a little bit in the last couple of years, and this is also a very popular topic of research these days because people are concerned about the future of energy generation utilization on our planet. And, one way to get energy cheaply would be if you could use solar photons to split water into hydrogen and oxygen, and you could burn the hydrogen in air with the oxygen, get the enthalpy out again. You'd be converting solar energy to enthalpy that way, for example. And so there's a lot of research on the idea of splitting of water by various kinds of metal complexes. And we were looking at some of these articles, Jack's article, where these guys take a ruthenium system, not totally dissimilar to some of the ones we've made in the past. And we realized that they have on this ruthenium system this ligand here. It has a pyridine in the middle, and it has a pair of benzimidazoles, one on each side, flanking the pyridine. This is a very effective tridentate ligand for ruthenium. It turns out, actually, that most people who make and use these ligands have to cite our work because we were one of the pioneers in this chemistry. And so today, if you want to buy the parent ligand, which has hydrogens on here from Aldrich Chemical, you can pay Aldrich Chemical, they'll sell it to you $60 for a gram. And I love it when you do that because they buy it from me. I sell it to Aldrich. Unfortunately, they don't give me $60 a gram, considerably less, but anyhow. And what one can do is you have a nice reactive unit here, position where you can perform substitution and functionalization. Various kinds of R groups can be put on. So, it's obvious that what one can do is put something nice on. And Mohammed has now put on here, onto those nitrogens, anthracene groups. And the idea is that we start putting on absorbing chromophores like this, where our goal here is to just try and make these stronger absorbers of wavelengths where there are lots of photons in order to funnel energy to the ruthenium that we would chelate, because the whole point of these compounds, one of the reasons I should say that people are interested in them is that when you capture a photon and the energy is funneled to ruthenium, the ruthenium complex kicks out an electron. And you can use that electron, for example, to reduce water to hydrogen. And there are some cycles that do this fairly effectively with a quite low efficiency, unfortunately. So you see we've successfully attached the anthracenes, and if you rotate this molecule, picture 90 degrees around a vertical axis, we see that these anthracene groups are sort of anti-parallel to each other. And you have the benzimidazole on the left, the pyridine in the middle, and the benzimidazole on the right. And so you still have, of course, the appropriate structure to chelate something like iridium, or ruthenium, or whatever you think the metal might be that will solve the world's energy problems. And in fact, these molecules in the crystal lattice, these ligands that we've made, they actually stack. There's a pi-pi stacking of anthracenes pairwise in the molecules. And pairwise, this kind of stacking, by the way, I mean, it's at least pairwise. I'm not sure whether it goes on in the lattice. But this kind of pi stacking turns out to be of potential interest in structural chemistry for practical applications. For instance, we have another system in collaboration with some of my overseas collaborators. This is these molecules. The green represents a terbium cation, and we see that we have, in this picture, I think we have 1, 2, 3, 4, 5, 6, 7, 8, 9 of these molecules. And you notice, for example, that if you look at this terbium here, it's connected to a ligand, which is then adjacent, it's pi stacked, pi interfaced to one of the ligand arms of the next molecule. And that is, in turn, is pi stacked onto one of the ligand arms of the next molecule, to the next one, to the next one. And so these molecules form an infinite pi stack. The individual molecules are luminescent. And so what happens here is we've been able to generate from these molecules, in effect, a super antenna of a kind that it's not clear to us has any precedent in chemistry, except I have to say I do know one example of this in chemistry, and it's called photosystem 1. It's called the chlorophyll photosystem for capturing light and converting long wavelength solar light into energy. So we're actually, I have to tell you, we're still trying to understand how this system works, because there are not a lot of things like this in the literature that make it easy to go and say, oh, it's just like this one, just like that one. It's tough to understand it. So working backwards in time, here are a couple of current denizens in my lab. Eric Duranza here making some isoindolines, actually. And the isoindoline, they are yellow, and this one looks like it might be glowing a bit in the light of the flash gun. So some of these isoindolines themselves are also luminescent. And Adam Meisel on the other side here is carrying forward some vanadium chemistry that was done by a Fulbright scholar visiting my lab. We go back a little bit further in time. There'll still be some people you recognise here, I think. So, you know, sometimes what happens is other graduate students, other groups will wander into my lab, and when they do, there's one there, you know, what we do is we lock the door. We shackle them to the bench and make them analyse some spectra before we let them go home or give them any bread and water for the next 2 days. And Dr. Molly's standing here and she's looking a bit bewildered. And she's saying, my God, I'm going to go chiral. And she did. And so this is some of the other kind of work we've been doing, looking at chiral metal complexes, some circular dichroism, kindly obtained for us by John Soffer in Dr. Schweitzer-Stenner's lab. And going back a bit further in time, here's a colleague of mine. His name's Max, working in my lab. Now, if you look at Eric and Adam in the lab, you notice they're wearing their eye protection. They've got their lab coats on. And Eric's just had the top off, so he's got his gloves on. But Max, you know, Max is very naughty. He's got some eye protection. He's got no lab coat, no gloves. And so this guy will get into trouble in the lab at Drexel. By the way, I don't know if you know who this was. It turns out he had a student who became well known. The student's name was Francis Crick, actually. And he and an American colleague named Watson did something, I don't know, with calf thymus and salmon spermatozoa and made some interesting comments about the nucleic acid molecules or something like that. So anyhow, that's enough. That's all for now. Thanks.